Let's go ahead and see if this setup is working. Let's do a quick audio check. And it looks like everything is fine audio-wise. Is video functioning just fine? Yep, I can see my hand moving. Okay, we are good to go. All right, so the plan for today is just going over some problems that I assigned to a student of mine because, well, it's not like I have any chatters asking questions. It's probably going to take a while for that to happen, so in the meantime, I have to come up with stuff to cover every week. So, yeah, for this week, it's going to be some rotational dynamics, which is pretty far into your typical physics course. So those who are new to physics, I'm sorry, but a lot of this is way beyond what you're going to be able to follow. But who knows, maybe if you stumble upon this and you're interested enough, maybe you'll still glean something from this. I don't know what exactly, but it is what it is. Anyway, I'm going to unplug these headphones because I don't really need them anymore. I already did my sound check. And headphones tend to hurt my ears if I wear them for too long, so putting those away. Oh, I probably should have moved this to the side beforehand, but oh well. Let's go ahead and move this out of the way. Maybe 45 minutes wasn't enough prep time after all. Okay, I think that should be enough to do the trick. Alright, so today we're going to be doing some rotational dynamics problems, and in case you're wondering where these problems come from, they are coming from this book right here, College Physics, 7th edition, Volume 1, from Surway and Fawn. I bought this for, I don't even remember, somewhere between $10 and $20 as a used copy, if you want to get a hold of that. If you want a free physics textbook, you can look up the book from OpenStax. If you just go into Google and type OpenStax, spelled with an X, and then also just add physics into your search, and you'll see all of their free physics books, which you can either just use on their website or download for yourself to use offline. So yeah, those are your options if you don't have your own physics textbook. But without further ado, let me go ahead and look at the problems that I wanted to go over for today. So to start us off, looks like I have problem 33. I'll show the book if I can actually fit it onto the screen whenever there's a relevant diagram. If not, then I'll just try my best to redraw what they have. But yeah, so 33 says, a cylindrical fishing reel has a moment of inertia of 6.8 times 10 to the negative 4 kilogram meters squared, and a radius of 4 centimeters. So we've got ourselves a cylindrical fishing reel, cylinder shaped, a cylindrical fishing reel. I probably should have drawn it a little bit bigger, but oh well. It has a radius of 4 centimeters, so radius is 4 centimeters, and its moment of inertia is equal to 6.8 times 10 to the negative 4 kilogram meters squared. Let's see. A friction clutch in the reel exerts a restraining torque of 1.3 Newton meters if a fish pulls on the line. The fisherman gets a bite, and the reel begins to spin with an angular acceleration of 66 radians per second squared. The questions are, Part A, what is the force exerted by the fish on the line? And Part B, how much line unwinds in 0.5 seconds? So let's copy down the other data that they gave us and do some rereading. So when a fish tugs on the line, there's going to be a restraining torque due to friction. So torque due to friction is equal to 1.3 Newton meters. And when the fisherman gets a bite, the reel begins to spin with an angular acceleration of 66 radians per second squared. So the angular acceleration is 66 radians per second squared. All right, so questions were, Part A, what force is exerted by the fish on the line? And Part B, how much line unwinds in 0.5 seconds? Part B, how much line, so I guess the length of the line in 0.5 seconds. I'm just going to use S as the variable for the length of line that unwinds. Okay, let me complete the drawing then. So we have this fishing reel. It's going to have a line that extends into the water, and somewhere at the end of that line is a fish that has bitten onto the line and is pulling at it with some amount of force. So the fish is pulling with some amount of force. We'll call it the force of the fish. And that is going to create some sort of tension in the fishing line. So that's going to create some sort of force of tension in the fishing line, and that same force of tension acts on the fish as well. And there's also going to be some sort of torque due to a, what do they call it, a friction clutch? Yeah, a friction clutch built into the fishing reel. All right. I think we have all the ingredients we need in order to work this out. So the force exerted by the fish. Let's see. If the fish accelerates along with the line, then the acceleration of the fish must be the same as the tangential acceleration of the line. So I guess that's the first thing I want to calculate. A tangential is going to be the radius times the angular acceleration in radians per second squared. So radius is in centimeters. I'm going to convert that to meters. So that's going to be 0.04 meters times 66 radians per second equals 0.04 times 66. I'm getting 2.64 meters per second. So 2.64 meters per second. Or per second squared, I should say. 2.64 meters per second squared. So that must also be the acceleration of the fish. So I can write a Newton's second law expression for the fish. Net force on the fish equals, well, I guess we don't really know the mass of the fish, do we? So how are we supposed to figure out maybe they just intended for us to just assume that the force exerted by the fish is equal to the force of tension, but that would... Maybe I am overthinking this problem. I'll just write out what I'm thinking and we'll see whether or not it's overthinking the problem. So we'd have the mass of the fish times the acceleration of the fish, which is the same as the tangential acceleration of the reel, which is 2.64, equals the... Actually, wait. No, I am overthinking it, because the force that the fish exerts on the reel is the tension force, and then the reel exerts an equal amount of tension force on the fish. Yeah, this would be the force of the fish right here. Yeah, I'm overthinking this. Okay, we don't actually need that. Never mind it. Let's see. Then where do I want to go from here? If I already have the tangential acceleration of the line, then I guess we can write a net torque equation for the reel itself. So let's see, net torque on the reel equals, I'm going to say it's the sum of the counterclockwise torque caused by the force of tension, also known as the force with which the fish pulls, minus the torque due to friction, which would have to be then in the clockwise direction. So I'm going to say it's the torque due to tension or torque due to the fish, either way you want to look at it, minus the torque due to friction equals the moment of inertia of the reel times the angular acceleration of the reel. So for the torque of the fish, we'll figure that out in a minute. The frictional torque is 1.3 Newton meters, and then we've got just the numbers they gave us, 6.8 times 10 to the negative 4 for the moment of inertia, times 66 for the angular acceleration. Let's see, 6.8 times 10 to the negative 4 multiplied by 66 gives me 0.04488. So hardly anything, 0.04488. If I add 1.3 to both sides, then that leaves us with the torque due to the fish is equal to 1.34488 Newton meters. All right, and then the other formula for the torque due to the fish would simply be the basic torque equation. Torque due to a force is equal to the lever arm times that force times the sine of the angle between the force and the lever arm. So the lever arm is from the axis of rotation to the point where the force is applied. So from the axis of rotation, which would be the center of the reel, out to the point where the force is applied, which is on the rim of the fishing reel. So that's your, that also indicates your direction, points that way for the lever arm, straight out. The tension force is going to be tangent to that rim, so they make a 90-degree angle with each other. So we've got R, which is going to be 4 centimeters, 0.04 when converted to meters, times the force of the fish, or the tension force in the reel, in other words, times the sine of 90 degrees. And of course, if you've done this enough times by now, you already know sine of 90 degrees is 1. So substitute in 1.34488, 1.34488, divide by the 0.04, and let's see what we get. 1.34488 divided by 0.04 is about 33.622. The force exerted by the fish is equal to 33.622 newtons. Okay, there we go. And for the fish to have an acceleration of 2.64 meters per second squared, which I guess I didn't really need to calculate. Actually, we do, because we need it for part B. But in order for the fish to have this acceleration, there have to be some other forces acting on the fish, because I already crossed that out. The force exerted by the fish acts on the reel, not the fish. You've got the tension force acting on the fish. There must be some other force acting this way on the fish, probably due to just the fish kind of trying to swim backwards and pull. I guess we could call it the force of the water, if we don't want to be too specific about it. And that has to be enough force to overcome this tension force that's pulling on the fish, which happens to be 33.622. So the fish has to have some force greater than 33.622 in the opposite direction. How much greater? Well, that depends on how much mass the fish has, and since we don't know that information, we can't investigate that any further, but, you know, food for thought, so I figured I'd mention it. Okay, that's part A done. Part B, how much of the fishing line gets pulled out in 0.5 seconds. So two different ways you can do this. You can either calculate the angular displacement first, then you can do S equals R times delta theta. So that's one way you could do it. Or you could do what I did, which is convert the angular acceleration into tangential acceleration and use that instead. So you could either do, delta theta equals omega initial times t plus 1/2 alpha t squared. You know omega initial is 0 because the fishing line starts with 0 rotation. It starts from a non-moving state. And you already know alpha, and t is given as 0.5, so you could do that. Or you could use S is equal to v tangential initial times t plus 1/2 acceleration tangential times t squared. V tangential initial, of course, is going to be 0 as well. So both of those are zeros. I might as well write them in there. Both of those are zeros. I already calculated the tangential acceleration, so I'm going to go with this one. But it's literally the same thing no matter which route you take. In my case, I multiplied by the radius ahead of time. In this other route, you would multiply by the radius at the end. So it's really just a matter of the order of the steps, but you have to take the same steps in the end either way. It's like turning north and then east versus turning east and then north. Anyway, where was I? Right, so calculating the amount of line that has been pulled out, it would be 1/2 times 66 times 0.5 squared, which is, let's see, a half times 0.5 squared is 1/8, so 66/8 gives me 8.25 meters. 8.25 meters of fishing line. And there we go. That takes care of number 33. All right, next up is 35. So for 35, it says we have a 150 kilogram merry-go-round. I might as well put up the next sheet for that. We have a 150 kilogram merry-go-round in the shape of a uniform, solid, horizontal disc of radius 1.5 meters. So let's go ahead and draw that. Okay, and it has a radius of 1.5 meters, and it weighs 150 kilograms. Mass is 150 kilograms. It's set in motion by wrapping a rope around the rim of the disc and pulling on the rope. What constant force must be exerted on the rope to bring the merry-go-round from rest to an angular speed of 0.5 revolutions in 2 seconds? So there's a rope tied around this thing. There's a rope tied around this thing. Goes around along the back. I guess I'm supposed to be drawing it touching the rim all the way, but just to make it visible, pushing it a little further back, and then yeah, there's some sort of pull on that rope, like so. Let's reread. So it says, what constant force, I'm just going to call it a tension force, must be, where did it go? What constant force must be exerted on the rope to bring the merry-go-round from rest to an angular speed of 0.5 revolutions per second in 2 seconds? So from rest to an angular speed of 0.5 revolutions per second in a time of 2 seconds. All right, first off, what I want to do is I want to convert my revolutions per second to radians per second, because most of my equations only work in radians. So what I'm going to do is I'm going to take omega final over here equals 0.5 revolutions for every 1 second, and I'm going to convert every 1 revolution, every 1 full rotation is equal to 2 pi radians, which is the equivalent of 360 degrees. So revolutions cancel out and we get radians, so 2 pi times 0.5 just leaves us with pi, so that's pi radians per second. And I guess you can plug in the value of pi, but let's save that step until later. We don't want to make our numbers look too ugly just yet. Let's see. So I'm going to write that that's pi radians per second. And let's go ahead and do the kinematics aspect of it first. So I want to get my angular acceleration, and I have 3 of my kinematic variables, so that's all the information I need to calculate the other 2. The one I want is the angular acceleration, so first equation should serve us just fine. Omega final equals omega initial plus alpha times t. Omega final is pi equals omega initial is 0 plus alpha is unknown and t is 2. So alpha equals pi over 2. And that's going to be in units of radians per second squared. All right, now that we have this, we can get closer to figuring out the force. To figure out the force, we need to figure out the torque that it produces on this merry-go-round. So let's go ahead and write net torque equals moment of inertia times alpha. So I guess we need to calculate moment of inertia now. Moment of inertia, this thing was described as being in the shape of a uniform solid horizontal disk. Uniform solid horizontal disk. And you can just look up the formula for the moment of inertia for a disk. If it's a solid disk, then its moment of inertia is 1/2 of its total mass times its radius squared. So in our case, it's going to be 1/2 times 150 times 1.5 squared. Okay, half of 150 is 75, and then 1.5 squared is 2.25, so 75 times 2.25 is 168.75. 168.75 kilogram meters squared. We know it's kilogram meters squared because we multiplied mass in kilograms by meters squared. Kilogram meters squared. It's as simple as that. Now we can plug that in over here to get our net torque. So we figured out the right-hand side of this equation, essentially. Now what about the left-hand side? So did they mention anything? They didn't mention anything involving like friction with the axle or anything like that. So I'm going to assume that this tension force is the only force creating a torque on this merry-go-round. So then our net torque is our only torque, is the torque due to tension. Torque due to tension is equal to 168.75 times pi over 2. And I guess we might as well plug in our numbers now to see what that amounts to. 168.75 times pi over 2 is 265.07. 265.07. For those of you worried about sig figs, I don't really pay much attention to sig figs when I'm doing physics. That's more of a concern for chemistry students. With physics, you'll do your sig figs when and if you end up working for NASA, because then getting it wrong will cost billions of dollars in destroyed rockets that never make it to outer space, and we definitely don't want that. But this isn't NASA, you're just doing a physics problem, so it's not so serious. Anyway, where did I want to go from here? Oh, right, torque due to tension. So we've got 265.07 Newton meters is the torque due to this tension force. So the formula for the torque due to a force is, again, lever arm times the force. So torque due to tension is equal to lever arm times the force of tension times the sine of the angle between the directions of those two vectors. The lever arm points from the axis of rotation to the point where the force is being applied. The tension force is being applied at this point, so the lever arm is from here to here. And if I drew it well enough, it would be a lot clearer that this is supposed to be a 90-degree angle. So we've got 1.5 times the force of tension is currently unknown, times sine of 90 degrees, which of course we know is equal to 1, so it doesn't really do anything here. And that's equal to this. So 265.07 is equal to 1.5 times the tension force, divide by 1.5, and we're done. 265.07 divided by 1.5 is 176.71. Force of tension is 176.71 newtons. All right. And that's the end of that problem. Next one I have lined up is 39. And what does 39 say? It says, let me get a new sheet out first. It says, a 10-kilogram cylinder rolls without slipping on a rough surface. At an instant when its center of gravity has a speed of 10 meters per second, determine the translational kinetic energy of its center of gravity, and also determine the rotational kinetic energy about its center of gravity and its total kinetic energy. All right, so we have cylindrical object, something like maybe a can. Let's see, how do I want to draw this? Something like that. It's rolling along the ground. I don't know. I don't like the way I drew this thing. Maybe if I... How do I want to draw this? Something like that. We'll say that this whole parallelogram thing that I drew is like a patch of earth that this can rolls along. So they said it's 10 kilograms. They did not mention its radius or its mass. So I guess those are not going to be... Oh, wait, what am I saying? They just mentioned its mass, but they didn't mention its radius. So I'm going to guess that's not going to matter. Just a hunch. All we know about it is that it has a mass of 10 kilograms. Let's see. All we need is its kinetic energies. So, the translational kinetic energy of its center of mass is the first thing they want. Kinetic energy translational. Some of you probably just write this as K. I I use KE because it's what I've gotten used to. And I guess some teachers will even have their students call this E, which is also fine, but as long as we know what we're talking about, the labels that we use for our variables can change. Translational kinetic energy is going to be 1/2 the mass times the speed of the center of mass squared, which is also equal to the tangential speed. So speed of the center of mass is equal to the tangential speed of the what would you call it? The edge of the cylinder. My goodness, my brain is malfunctioning today. Maybe I didn't get enough sleep. Actually, I'm pretty sure I did. Anyway, I lost my train of thought. That happens a lot with me. What was I doing? Okay, so 1/2 m times v tangential squared. Well, we were already given v, which is 10, so actually we can calculate this right away. 1/2 times 10 is what they gave us for the mass, and for the tangential, well, they called it the velocity of the center of mass. Velocity of the center of mass, they gave us as 10 meters per second, so I can go ahead and plug that in for my v tangential. And there we go. 1/2 times 10 times 10 squared. Half of 10 is 5, and then 10 squared is 100. 5 times 100 is 500 joules of translational kinetic energy. Okay, part B is asking for the rotational kinetic energy. Kinetic energy rotational. That's equal to 1/2 moment of inertia times angular speed squared. The moment of inertia for a solid cylinder, we just had the formula in the previous problem. It's 1/2 its total mass times its radius squared. So I, for a cylinder or disk, a disk is really just a thin cylinder, is 1/2 of its mass times its radius squared. So we're going to do 1/2 times 10 times, well, we don't know the radius, so we'll just keep it as r. We can take care of that r problem because we can also replace the angular speed. The tangential speed is equal to the radius times the angular speed. I guess I'm going to use capital R this time for our unknown radius. So we can replace omega with, if we divide both sides by r, we can replace it with v tangential over r. So if I go ahead and do that in here, then I'm left with kinetic energy rotational equals 1/2 of 1/2 times 10 times r squared times omega squared is going to be v tangential over r, and then that whole thing squared, which just means v tangential squared over r squared. And r squared divided by r squared cancels out, and v tangential squared is v center of mass squared, so we can just plug in 10 for that, and we've got 1/2 times 1/2 times 10 times 10 squared. Half of a half is a fourth, and a fourth times 10 is 2.5, and then 2.5 times 10 squared. So that's 100. 2.5 times 100 is 250 joules. And then part C is the easiest part, given that you completed parts A and B. What is the total kinetic energy? Kinetic energy total is just the translational plus the rotational. I imagine most of you don't need me to tell you this, but just for the sake of completion, 500 plus 250 gives us a total of 750 joules of energy. All right, there we go. Next up is problem 41. What does 41 say for us? 41 says, a horizontal 800 Newton merry-go-round of radius 1.5 meters is started from rest by a constant horizontal force of 50 newtons applied tangentially to the merry-go-round. So pretty much this scenario that we had drawn over here, they're pulling with a force of 50. Okay, lost my place. It was, okay, find the kinetic energy of the merry-go-round after 3 seconds. The kinetic energy of the merry-go-round after 3 seconds, and it says in parentheses, assume it's a solid cylinder. Okay, so it shouldn't be that hard, but I'm trying to see if we have more than one way of solving it. So we could go for getting its moment of inertia, calculating the torque on it, and getting its angular acceleration that way, and then doing some kinematics to figure out its final rotational speed, and then use that to calculate its final kinetic energy. Or could we just use the work equation? Let's see. Yeah, we do have 2 routes, but one is one uses a technique that most teachers don't really cover, so I might want to avoid that. I think I can fit this one into here, but we'll see. I might end up needing a new sheet of paper after all. So it's an 800 Newton merry-go-round. So mg equals 800 newtons. Divide by g to get its mass, which you then need to use to get its moment of inertia. Radius equals 1.5 meters. There is a force exerted on it of 50 newtons, and it's pretty much exerted in the same way that this one is, tangent to it, so that the torque resulting from it is just going to be the radius of the merry-go-round times that pulling force times, it's going to be 90 degrees again, which just gives you a 1 over here. So that tells me that the torque we're going to get from this thing is equal to R times, they said it was 50 newtons of pulling force times sine of 90 degrees, which again is just 1. Find the kinetic energy of the merry-go-round after 3 seconds. They gave us t equals 3 seconds. And they want the kinetic energy of the merry-go-round. So the merry-go-round is just going to spin in place. It's not going to move, so all of its kinetic energy is going to be rotational kinetic energy this time. And that's what they're asking us to find. Okay, since that pulling force is the only force that's creating a torque on this merry-go-round, it must amount to the net torque. So net torque is equal to, let's see, 1.5 times 50 times 1. 1.5 times 50 is 75 Newton meters. This is equal to the moment of inertia of the merry-go-round times its angular acceleration. The moment of inertia is going to be, again, the disk formula for moment of inertia, 1/2 of its mass times its radius squared. So that's going to be 1/2 times, well, its mass is going to be 800 over g. And then times its radius squared. 1.5 squared is 2.25. And then times alpha. And let me actually change colors because this is all starting to look all jumbled together. Let's see, so 1/2 times, I'm looking for any simplifications I can do, but I'm not spotting anything. So 1/2 times 800 is 400. 400 times 2.25, and then over g. So over 9.8 is the value of g, and that's 91.8367. I'll round that to 837, so 91.837. 75 equals 91.837 times alpha. So if I divide 75 divided by 91.837, I'm getting 0.8166. So that's going to be alpha equals 0.81, I'll round it to 7 radians per second squared. Okay, and it looks like I am going to need some more space, so let's continue on another sheet. Let's see, I want to copy angular acceleration equals 0.817 radians per second squared. Not the best looking 8 I've ever written, but it'll have to do. And let's see what we can do with this. So they told us that it started from rest, didn't they? Let me reread it. Yeah, it started from rest, so we know that omega initial is 0, and they gave us t equals 3 seconds. We need to get omega final, so given these three, we can calculate using the first equation of kinematics again. Omega final equals omega initial plus alpha times t. So that's a 0. Omega final is what we're trying to solve for, and 0.817 times 3 is all there is to it. 0.817 times 3, 2.451. I'm just going to round it to 2.45. 2.45 radians per second. Now that we know this, we can calculate the final rotational kinetic energy. So that's going to be 1/2 times, oh, come to think of it, I guess we could have avoided substituting the moment of inertia until this point. That was an oversight on my part. 1/2 I times omega final squared. Omega initial was 0, so there was no initial rotational kinetic energy. So we've got 1/2 times 1/2 times 800 over g times 1.5 squared was 2.25 again, and then all that times 2.45 squared. Let's see. 1/2 times 1/2 is 1/4. 1/4 of 800 is 200, and then 200 times 2.25 over g over 9.8 is 45.918. So we've got 45.918 times 2.45 squared. 45.918 times 2.45 squared, and that is a grand total of 275. It says 622, so I'm going to round that to 62 joules. I keep mentioning the next digit after the digit that I round to because I know it is very common for students to assume that rounding is a simple matter of dropping the last digit. It's not as simple as that. You have to remember to round up if the next digit is a 5 or higher. A lot of students forget that for some reason. And that's 41. Next up is 42. So 42 says, a car is designed to get its energy from a rotating flywheel with a radius of 2 meters and a mass of 500 kilograms. So radius of 2 meters and a mass of 500 kilograms. If it has a radius of 2 meters, that's quite big. How does that even fit inside the car? That would mean the car would have to be at least 4 meters wide or 4 meters tall if the flywheel goes like through the middle of the car between all of the car seats, which I don't see happening. If anything, it would be under the car. 4 meters wide, that is a lot. Huh. Anyway, it's got a radius of 2 meters and a mass of 500 kilograms. Before a trip, the flywheel is attached to an electric motor, which brings the flywheel's rotational speed up to 5,000 revolutions per minute. So, at the start of the trip, this thing has an initial 5,000 RPM, revolutions per minute. I'm just going to write that as revolutions over minutes, which I'm going to convert pretty soon. Find the kinetic energy stored in the flywheel, and then part B, if the flywheel is to supply energy to the car as a 10 horsepower motor would, find the length of time the car could run before the flywheel would have to be brought back up to speed. Okay, so part A first, it says find the kinetic energy stored in the flywheel. So easy enough, kinetic energy. Rotational is just 1/2 of the moment of inertia times the angular speed squared. Come to think of it, they didn't mention anything about a final speed, but we're just going to go with the initial speed that they gave us. However, there's one little twist here. Our units need to be converted. This needs to be converted into radians per second in order for us to get joules. So let's go ahead and do that conversion. 5,000 revolutions for every 1 minute. We need to convert the revolutions to radians, which is something we've seen before. Every 1 revolution is equal to 2 pi radians. If I divide 2 pi radians by 1 revolution, since these are equal to each other, this whole thing is just equal to 1. So yes, I'm allowed to multiply by this fraction. It doesn't change the quantity that I'm working with. Let's see. Next up is converting the minutes to seconds. So every 1 minute is equal to 60 seconds. So that gets rid of minutes and leaves us with seconds on the bottom. So we've got radians left in the top, seconds in the bottom, which is exactly what we want. 5,000 times 2 pi over 60. I think I'm going to go ahead and plug in the value of pi this time. So 10,000 pi, if I do 5,000 times 2, that's where I'm getting the 10,000 from. So 10,000 times pi, and then divide all that by 60. And I'm getting 523.5987. I'm going to round that to 523.599. 523.599 radians per second. And then for the moment of inertia, they didn't really tell us the exact shape, but given the description of a rotating flywheel, I'm going to assume it's in the shape of a disk. I'm going to assume it's in the shape of a disk. What color do I want to use here? Let's go with green. So I of the flywheel is going to be 1/2, so I disk is 1/2 mr squared, so it's equal to 1/2 times 500 times the radius was 2 meters, so 2 squared. Half of 500 is 250. 250 times, that'll be 4. 250 times 4 is exactly 1,000 kilogram meters squared. And now we have everything we need to calculate the rotational kinetic energy. Rotational kinetic energy equals 1/2 moment of inertia, 1/2 of 1,000 times the angular speed squared, 523.599 squared. That's definitely a job for a calculator. 1/2 of 1,000 is 500, and 500 times 523.599 squared is a very, very big number. I'm getting, let me actually just write it in scientific notation. That would probably be for the best. I'm just going to round it to 3 decimal places, I think is enough, is 1.371 times 10 to the 8 joules, or 0.1371 gigajoules, if you will. 0.1371 gigajoules. It's not common to see such big energy units in physics. Usually this is more of something you see in chemistry, and even in chemistry, usually you're seeing kilojoules and not gigajoules. But okay, so that's part A. Part B, if the flywheel is to supply energy to the car as a 10 horsepower motor would, find the length of time the car could run before the flywheel would have to be brought back up to speed. So this is actually pretty easy unless you have forgotten the concept of power from the work and energy chapter of your physics course. Or if you just haven't had any physics at all, in which case, why are you even here? But I guess curiosity in the world of physics is a healthy thing overall, so I don't want to discourage that too much, but you really should learn the essentials before you tackle this. Anyway, 10 horsepower, they said. They said power, they want it to act as a 10 horsepower motor. They said 10.0 horsepower for those of you who care about the sig fig rules, but I'm just going to write 10. So 10 horsepower. Every 1 horsepower is 746 joules. Every 1 horsepower equals 746 joules. Or wait, joules? No, watts, I should say. Watts. Which is a joule per second. Right? Wait, I feel like I might be getting that wrong. Let me double check with Google real quick. Let's see. Horsepower to joules. Or not to joules, to joules per second. Yeah, 746 or 745.7 if you want to be more precise. But 746 is good enough for our purposes. Okay. Doesn't hurt to double check. Anyway, 10 times 746 is 7,460. So 7,460 watts. Or as I prefer to call it, instead of watts, I call it joules per second. Calling it joules per second has 2 benefits. The first benefit is that you don't have to write a W as the units for your power. The W can easily be confused with the symbol for work. So you're avoiding that confusion. And the other bonus is when you write it as joules per second, you can see from the units exactly what you're supposed to do next. If you have this many gigajoules of energy, or this much if you keep it in joules, and you're expending it at a rate of this many joules per second, then you already know how to get the amount of time that this motor will run before it needs to be recharged. Or, if you don't remember that, I guess you could also memorize that power is equal to work over change in time. And then you can remember that work is equal to the change in kinetic energy. So change in kinetic energy over change in time. Change in kinetic energy, you want your kinetic energy to completely run out. So your final kinetic energy is 0. Your initial kinetic energy is this much. So negative 1.371 times 10 to the 8 joules divided by the total time equals the power output of 7460. So you could do it just through remembering a bunch of equations instead, but you don't have to. If you remember that watts are joules per second, then it becomes so much more obvious. You can do it as a sort of unit conversion like this. And that's what I'm going to do. So I'll write it here since I seem to have just enough space. We've got 1.371 times 10 to the 8 joules multiplied by, let's see, every 7460 joules is 1 second of energy consumption. So joules cancel out and you're left with seconds. And I guess I'll write my equal sign over here. 1.371 times 10 to the 8 divided by 7460. 1.371 times 10 to the 8 divided by 7460 is a much more reasonable number. I'm getting, let me switch that back to normal mode instead of scientific mode. I'm getting 18,378 seconds. 18,378 seconds, which is not very intuitive for us. So let's divide it by 60 to see how many minutes that is. That's 306.3 minutes. If I divide that by 60 again, that's 5.1 hours. 5.1 hours. 5.1 hours. Which is actually pretty good. But again, it requires this really big flywheel that, correct me if I'm wrong, but if it has a radius of 2 meters, it feels like it's too wide for any normal road. I mean, 2 meters, that's more than 6 feet. The radius of that thing is taller than me. And that's just the radius. You need to double that to get the minimum width that the car would have to have. Anyway, let's move on to the next one. Actually, let me take a sip of water first. Alright, that feels better. What was the next one? Next one is actually 43, so these next few are actually going to be in sequence. It says the top in the figure has a moment of inertia of 4 times 10 to the negative 4 kilogram meters squared and is initially at rest. I guess I can try and show you the figure. Let's see if this can actually show up on the screen. The way I have this thing angled, it's not always easy to fit in the whole book. Anyway, yeah, there it is. It's just a spinning top. That's all there is to it. They've got a force that's being applied tangential, kind of like what we saw twice now with the merry-go-round being pulled tangentially by a rope. Kind of the same deal going on here. So we have that spinning top. It has a moment of inertia of 4 times 10 to the negative 4 kilogram meters squared, and it starts from rest. It is free to rotate about a stationary axis, A prime. I don't know why they labeled it that way, but okay. Basically, they have, in the drawing, they've got a point A and another point A prime, and then they've drawn the axis between those 2 points. They could have just said an axis down the along its axis of symmetry. They would have conveyed the idea much more intuitively, I think, if they had just worded it that way. But now I'm just splitting hairs. Anyway, a string wrapped around a peg along the axis of the top is pulled in such a manner as to maintain a constant tension of 5.57 newtons in the string. If the string does not slip while wound around the peg, what is the angular speed of the top after 80 centimeters of string has been pulled off the peg. And then there's a hint that says, consider the work that is done. Okay, so they've got, I guess I'll draw it over here. They have some string wound around this thing, and some of it is being pulled on by some force. I'm just going to call it the force of tension. Well, actually, that's going to be an applied force, and then the reaction to it is going to be a force of, well, hold on. I might be wording that wrong. It's being pulled with some sort of force. The reaction to it is a tension force in this end of the string, and then there's going to be an equal tension force in that end of the string. So essentially what we have is tension force acting on the rim of the top part of the top. I'm not sure of a better way to word that, but it's basically the same as having a tension force acting on the rim of this sort of circular part that's used for spinning the top. Anyway, they tell us that the tension is 5.57 newtons constant. They also tell us that the moment of inertia of this thing, I don't have a formula for it, so I'm just going to have to take their word for it, is 4 times 10 to the negative 4. Very small. 4 times 10 to the negative 4 kilogram meters squared. And we're told that it's initially at rest. And is that all the information? No, they also said that this thing is pulled 80 centimeters outward. So they started here and then they pulled 80 centimeters and now it's here. So 80 centimeters or 0.8 meters is how I'm going to express it. We're going to want it in meters in order for our units to come out the way we normally expect them to. And that's all the information they gave us. That is all the information that they gave us. They did not tell us the radius of this thing, so we can't do what we did before. Since we don't know the radius, we can't calculate the torque. So we're going to have to adopt a different strategy here, and that's where the hint comes in. The hint is consider the work that is done. This is what I was referring to earlier when I was looking at, which problem was it? Was it this one? Or I think it might have been this one, where I mentioned that there's actually 2 different routes we could have taken with it, whichever problem that was. This is what I meant. So now we're encountering a problem that actually forces us to take that other route because we have no other choice. There is a way to figure out the final kinetic energy just by calculating the work done by the force. So, if you remember the work energy theorem, which you should because I just brought it up while talking about this equation over here, The work kinetic energy theorem tells us that the total work done on an object is equal to the change in that object's kinetic energy, also known as the kinetic energy final minus kinetic energy initial. Rotational kinetic energy is a type of kinetic energy, so this equation applies to it. So let's figure out the total work. The total work is going to be the sum of the work done by each and every force on this thing. So, there's a force of gravity acting down on it and a normal force acting up on it, but there's no displacement in the direction of either of those, so no work done by either of those forces. We can leave that out of the total. The only force left would be this force of tension. So we've got the force of tension of 5.57 newtons times the displacement of 0.8 meters times cosine of theta being the angle between the force and the displacement. The displacement is from here to here, it's straight to the left, and the force is also straight to the left. The angle between left and left is 0 degrees. Cosine of 0 is 1. So that's the left-hand side of our equation. Change in kinetic energy. Kinetic energy final minus kinetic energy initial. Kinetic energy initial is 0 because the initial angular speed is 0. And that leaves us with the final kinetic energy. The final kinetic energy is all rotational and not translational at all. And the reason we know there's no translational kinetic energy here is because, well, the top just spins in place. It doesn't move while it spins. The axis of rotation is glued in place. Now, that's not actually how it works with a real top. With a real top, usually it moves around as it spins, but we're simplifying for the sake of having a decent practice problem that's not too overwhelming. So here, the final kinetic energy is all rotational kinetic energy. And we already know the moment of inertia because it was given to us. So we can calculate the final angular speed of this top. 1/2 times 4 times 10 to the negative 4 times omega final squared equals whatever that is. I guess I might as well, where's my calculator? There it is. Might as well go ahead and calculate that now. 5.57 times 0.8 is 4.456. 4.456. Okay, multiply by 2 to cancel the half, and divide by 4 times 10 to the negative 4. So times 2, and then divided by parentheses 4 times 10 to the negative 4. Do not forget your parentheses when dividing by a product. If you forget the parentheses, then what it'll do is it'll divide by 4 and then multiply the result by 10 to the negative 4, which is not what you want. Be careful with your calculators. Anyway, I'm getting omega final squared is 22,280. And if I take the square root of that, I'm getting omega final is 149.26. 149.26 radians per second. At least those are the units I should be getting if I got all of my other units into what they usually should be. Kilogram meters squared, check. Newtons, check. Meters, check. Okay. And yeah, that was the end of it. All it was asking for was the angular speed. after 80 centimeters of string has been pulled out. Next one is number 44, which says a 240 Newton sphere, 0.2 meters in radius, rolls without slipping 6 meters down a ramp that is inclined at 37 degrees with the horizontal. What is the angular speed of the sphere at the bottom of the slope if it starts from rest? Now, they didn't say whether it was a solid sphere or a hollow sphere. You should just assume that it's a solid sphere, although they really should have explicitly told you. If you see that on the AP exam for you AP students, then just write at the beginning of your solution, assuming a solid sphere, and that way they can't really mark you wrong if they wanted you to assume it was a hollow sphere, because you'd be clearly showing them that you paid attention to the problem and it didn't say. It didn't give any indication. Anyway, let's see if I can actually fit this in here. Gotta try and be conservative with my paper, even though I don't even know how many reams of paper I have sitting in my boxes. I'm gonna have to go and check. Actually, no, they're not in boxes, are they? I can't even remember where I put them. Maybe they're in a closet somewhere. I'll have to... Well, I mean, if I run out of paper, then I might find out tonight, but that doesn't look like it's gonna happen. My stack still seems to have about 20-ish pages. Anyway, 44, a 240 Newton sphere, so I'm going to try and make this look somewhat 3D. Let me draw the sphere first. And then draw the ramp underneath it. Yeah, there we go. If only I found the time to get this good with my pixel art. Maybe I'd actually have a game out, but oh well. I'm gonna have to make time for that someday, but today is not that day. 240 Newton sphere. So I guess if we divide that by g, we'll get the mass of it, so we can calculate its moment of inertia. It has a 0.2 meter radius, so its mg is 240 newtons, and its radius is 0.2 meters. It rolls 6 meters down a ramp that is inclined at 37 degrees. So this is a 37-degree angle, and it rolls 6 meters down the ramp. That means that this is your 6 meters. Which is not what we usually try to work with. It's asking what's the angular speed of the sphere at the bottom of the slope if it starts from rest. So we know omega initial is 0, and by extension v initial is also 0. And the question is, what is omega final? All right, so if we are assuming a solid sphere, moment of inertia of a solid sphere, I solid sphere. You can look this up in your book, or you can look it up online. For the AP exam, you're not expected to have this memorized, but it is 2/5 the mass times the radius squared. All right, so here what we want to do is actually apply conservation of mechanical energy. And that means we're going to have to look at the potential energy, which means we're going to have to look at the height. To figure out the height of this thing, we know that it rolls 6 meters down the ramp, so the height can be calculated from that 6 meters and this 37-degree angle. 37 degrees is very special in physics. It's your... oh, well, actually, it's not going to be that helpful here. It would have been more helpful if this was a 10. But 37 degrees is usually the angle for your 3, 4, 5 triangles, or your 6, 8, 10 right triangles. But here, I guess, we're not going to be able to take advantage of that. Okay, calculator it is. So the height is on the opposite side of this right triangle, opposite to where the angle is. So that's going to be, let's see, this over 6 equals sine of 37. Therefore, sine of 37 times 6 will give us that. So 6 times sine of 37 degrees, I'm getting about 3.61 meters. 3.61 meters is your initial height. Okay, then applying conservation of energy, we have at the top it's at rest, so it's all potential energy. mg h initial plus 0 translational plus 0 rotational kinetic energy equals, at the bottom, I'm going to set the bottom to my 0 of potential energy. So potential energy is 0 this time, plus kinetic energy, that's going to be 1/2 m v final squared, plus rotational kinetic energy, translational plus rotational, so 1/2 I omega final squared. I can expand this, so I can say mg h initial is equal to, that's going to stay as 1/2 mv final squared. This is going to become 1/2 times I is going to be 2/5 mr squared, so 2/5 m times r squared. And then omega final squared, well, we can use the relationship v tangential, which is the translational velocity here. V tangential equals r times omega. So we can divide by r. Omega equals v tangential over r. So omega final squared is v tangential squared over r squared. And the r's cancel out. And since everything in this equation has mass in it, we can divide the whole equation by the mass, and the mass also cancels out. And that v tangential squared is equal to this v final squared. So these are just like terms. So we have just one unknown left in this equation. We can solve it. So let's go ahead and do 9.8 for g times 3.61 is equal to 1/2 v final squared plus 1/2 of 2/5 v final squared. A half plus a fifth. Common denominator between those is 10. So 1/2 is 5 over 10, and 1/5 is 2 over 10. 5 over 10 and 2 over 10, that's 7 over 10. times, both of those are the same v final squared. And multiply by 10, divide by 7, and take the square root. And if I do that, I get, let's see, 9.8 times 3.61 times 10 divided by 7. I'm getting 50.54 equals v final squared. If I take the square root of 50.54, I get 7.109. I'm going to round that to 7.11. So v final equals 7.11 meters per second, but they asked for omega final. So all I have to do is divide by r. 7.11 divided by 0.2 meters. 7.11 divided by 0.2 leaves me with 35.55. So omega final equals 35.55, if I can fit it in here, radians per second. Okay, that definitely isn't the easiest to read. Let me actually rewrite it over here. Omega final equals 35.55 radians per second. Yeah, there you go. That's a lot more visible. And there we go. I didn't have to needlessly use an extra sheet of paper for that one. Next up, this one is actually a lot simpler than it looks at first glance. 45 says, a light rigid rod 1 meter in length rotates about an axis perpendicular to its length and through its center as shown in the figure. Two particles of masses 4 kilograms and 3 kilograms are connected to the ends of the rod. What is the angular momentum of the system if the speed of each particle is 5 meters per second? Neglect the rod's mass. Let me show you the figure if I even can. I don't know. I feel like my book is a little too... Oh, actually, yeah, I can squeeze it in there. So yeah, that's the figure that they have. Rod in the middle, they've drawn it in green, and connected to it are two masses. One is 3 kilograms, the other one is 4 kilograms, and yeah, there you go. They're 1 meter apart. And they said that that rod is rigid but light. They're saying it's light so that you can treat it as if its mass is very, very close to 0. The reason they want you to treat its mass as if it's very, very close to 0 is because that would bring down its moment of inertia. Essentially, they're telling you to neglect the moment of inertia of the connecting rod. So that's what that is about. In case you were wondering, you do not need to factor the moment of inertia of the rod into this. It is negligible for this problem. Anyway, I'll read it again. So it's 1 meter, a light rigid rod 1 meter in length rotates about an axis perpendicular to its length. Axis perpendicular to its length just means it's going through the page. And then on its ends you've got a 3 kilogram and a 4 kilogram object. It's 1 meter in length, which means it's 0.5 meters from each object. So each object is 0.5 meters from the axis of rotation, is the thing to remember here. Let's see. And yeah, they mentioned the two masses, which I've already drawn. What is the angular momentum of the system if the speed of each particle is 5 meters per second? if this thing is moving at 5 meters per second, and this thing is also moving at 5 meters per second. What is the angular momentum of the system? Angular momentum of the system is simply the angular momentum of object 1 plus the angular momentum of object 2. And for angular momentum, we have several different ways to calculate it. The most basic way to calculate the angular momentum of an object is the moment of inertia of that object times its angular speed. However, if the object is a point mass, and I would consider it a point mass if the axis of rotation does not go through the object. So in this case, the axis of rotation goes through the rod. It does not go through the 3 or the 4 kilogram objects. So I would consider those to be point masses. Technically, if they have some volume to them, you could do some calculus and do something a little bit more precise, but clearly they didn't give us enough information to do that, and even if they did, it's not really worth the hassle. We don't need to be that precise. So, long story short, I'm treating these as point masses, and if they are point masses, the moment of inertia for a point mass, this formula you do need to know for the AP Physics exam if you're taking it, is the mass times the distance from the axis of rotation squared. So then if we do that, we have L equals, for each point, is going to be m times r squared times omega. But wait, we've replaced omega with something multiple times today. That's right, omega is v tangential over r. So we can say mr squared times v over r. That cancels one of the r's. So we've got L equals mrv, or, as I like to write it, mvr. That way I can remember it as the word mover. So this is the better way to go for this one, because we've got the masses, we've got the tangential velocities, and we've got r. It's much easier than trying to calculate a moment of inertia and converting to an angular speed. We'd just be wasting time doing that. So yeah, use this formula for angular momentum instead. So this angular momentum is going to be in the counterclockwise direction, and so is this one. So they both are in the same direction, both are counterclockwise, so they add. So the total angular momentum of the system is going to be, let me switch colors. Is going to be, for that first one, it's 3 times 5 meters per second times r is 0.5 meters away from the axis, and plus the second one is 4 kilograms times also 5 meters per second times 0.5 meters away from the axis of rotation. 5 times 0.5 is 2.5. So 3 times 2.5 plus 4 times 2.5 is 7 times 2.5. 7 times 2.5 is 14, 3.5, so 17.5. 17.5 what? Let's see, that would be kilograms times meters per second times meters. That's kilogram meters squared per second. 17.5 kilogram meters squared per second. A lot easier than it looks at first glance if you know which version of the angular momentum formula to use. And of course, being able to derive it from the basic angular momentum formula is also helpful. If you know how to derive it, and you know how to derive it quickly, then you don't have to memorize as much. Next up is 46, which says, Halley's Comet moves about the Sun in an elliptical orbit, with its closest approach to the Sun being 0.59 AU. AU stands for astronomical unit. 1 astronomical unit is the average distance between the Earth and the Sun. And then they say its greatest distance is 35 AU. If the comet's speed at closest approach is 54 kilometers per second, what is its speed when it is farthest from the Sun? You may neglect any change in the comet's mass and assume that its angular momentum about the Sun is conserved. All right, so we've got the Sun, and then we've got Halley's Comet, which has its closest point to the Sun is there, and its farthest point from the Sun is all the way out here, not drawn to scale, because if I were to draw this to scale, it would take more than just this one measly sheet of paper. Right, we're talking about from 0.59 to 35. I would need basically like more than not more than, almost 70 times this length. That's not going to fit on one sheet of paper. So we've got 0.59. We've got a distance of 0.59 AU, astronomical units, over there. And over here, this point is an entire 35 astronomical units away. Done. If the comet's speed at closest approach is 54 kilometers per second, so if, when it's over here, if it is moving at v equals 54 kilometers per second, then how fast is it moving by the time it gets here? So I guess I'm going to call this v close, and I'm going to call this v far. And they say assume that angular momentum is conserved. So angular momentum initial of the comet equals angular momentum final of the comet. Okay, so we can just use this MVR formula to calculate its angular momentum yet again. The axis of rotation, well, I guess in this case it's not really a fixed axis of rotation since it's not a perfectly circular orbit, but the point that it's rotating around, wherever that axis is, it's clearly not going through the comet. So same argument I made over here, you can treat the comet like a point mass, so you can use MVR for its angular momentum. So if I do mv initial r initial equals mv final r final, the mass stays the same, so that cancels out on both sides. V initial, I'll say that this is the initial point, is 54 kilometers per second. Notice I did not convert it to meters per second. For this formula, you don't actually have to do that most of the time. and then 0.59 astronomical units, again, not converting that to meters. I don't have to, and it looks like I'm not going to have enough space on the right over there, so I'm just going to do it on the left. So 54 times 0.59 equals V far times 35 astronomical units. So yeah, here comes the reason why you don't actually have to convert this time, because astronomical units on this side cancel with astronomical units on that side. And if I'm left with kilometers per second on this side, then I better get kilometers per second on that side. So there you go. The units that you put in are the units that come out. As long as either the distance units or the velocity units match. If you've got two distance units and they match, then they can cancel out, and then your velocity unit will come out to the same units that your other velocity is, and vice versa. If you had two velocities that were in the same units and then one distance unit, whatever that is, that's going to be the distance unit that pops out on the other end of the equation. So this is one of the few instances where you don't have to be so nitpicky about your units. A breath of fresh air, but enjoy it while it lasts, because it doesn't last very long. 54 times 0.59 divided by 35. Where's my calculator? One of these days I'm going to lose this thing. It hasn't happened yet, but one of these days it just might. 54 times 0.59 divided by 35 is 0.91. So I'm getting V far equals 0.91 kilometers per second. All right, that leaves us with 3 more that I have on my list, and I've got about 15 minutes left on the clock. And here I was thinking that I was going to finish all these problems and still have to come up with more to fill the time. Let's see, next up I have number 49. Let me get some water first. Okay. 49 says, a solid horizontal cylinder of mass 10 kilograms and radius 1 meter rotates with an angular speed of 7 radians per second about a fixed vertical axis through its center. A 0.25 kilogram piece of putty is dropped vertically onto the cylinder at a point that is 0.9 meters from the center of rotation and sticks to the cylinder. Determine the final angular speed of the system. So we've got ourselves a cylinder. And its axis of rotation is just through its center. And a piece of putty or clay is dropped onto it. A piece of putty is dropped onto it. And where does it fall? let's see. It falls 0.9 meters from the center of rotation. So this is a 0.9 meter distance. That doesn't look too good. The 9 and the M are kind of fused together, but you know what it's supposed to say, 0.9 meters. And then they said the radius of the cylinder, I guess I'll draw that over here, is a full 1 meter. Let's see. So the piece of putty has a mass of 0.25 kilograms is what they said. And the cylinder itself, I'll give that a capital M. Cylinder is equal to 10 kilograms. And it rotates with an initial angular speed of 7 radians per second. Omega initial equals 7 radians per second. Okay, so it's initially rotating at 7 radians per second. A piece of putty gets dropped onto it. What happens? Does it speed up? Does it slow down? Intuition would suggest that it slows down because you're putting more weight on it, is what most people would say if they didn't know the correct physics terminology. And this time your intuition would actually be right. So let's see what's going on. This is really just a conservation of angular momentum problem. How do I know that the angular momentum is conserved here? Well, the condition for angular momentum to be conserved is that the net torque external is equal to 0. If there's no net external torque being exerted on the system, then the angular momentum of the system is conserved. There's nobody that's deliberately interfering with the piece of putty or the cylinder to apply some sort of external force on it, therefore there is no external torque on it. There is a force when the two interact with each other. They exert friction forces on one another, but those are not going to create an external torque. Those are internal. They are equal and opposite torques resulting from equal and opposite friction forces between the two objects that act for an equal amount of time. So whatever change in angular momentum the piece of putty causes for the cylinder is going to cause an equal and opposite amount of change to the piece of putty. So across both of the objects, the total angular momentum is still the same. It's just that some of it moved from one of the two objects to the other, but it's still between those two objects. It didn't escape to like somewhere outside of that system. Anyway, where do I want to go with this? So let's go ahead and write angular momentum initial equals angular momentum final. And this time I'm actually going to use the base formula for angular momentum. Moment of inertia of the system initial times omega initial equals moment of inertia of the system final times omega final. I guess I should say omega system initial and omega system final here, but these are the only omegas in the problem, so I don't think there's going to be any confusion there. Over here, the moment of inertia of the system initially is just the moment of inertia of the cylinder. Initially, it's just the moment of inertia of the cylinder. The piece of putty isn't rotating around any axis at the beginning because it's still being dropped. It's not rotating around an axis. It doesn't have a moment of inertia. A moment of inertia is defined for objects around some sort of axis of rotation. So, yeah. Well, actually, it would be more accurate to say it doesn't have an angular momentum yet. That would be the more accurate thing to say because it doesn't have an angular velocity yet. Anyway, over here we just have the moment of inertia of the cylinder, which is, we need to calculate it, don't we? Yep. Let's go ahead and get that. So we've seen this formula so many times tonight, or today, depending on when you're watching this. Moment of inertia for a solid cylinder or disk is 1/2 mr squared. So we've got 1/2 times 10 kilograms times the radius of the cylinder is 1 squared. Half of 10 is 5, and 5 times 1 squared is 5. 5 kilogram meters squared. Okay, so moment of inertia is 5, omega initial is 7. Omega final here is going to be unknown, but what about the final moment of inertia of the system? This is going to be different from the 5 that we started with because now the piece of putty is involved. So now the moment of inertia of the system is moment of inertia of the cylinder plus the moment of inertia of the piece of putty. The piece of putty rotates around the axis of rotation once it attaches to this cylinder. The axis doesn't run through it, so we can treat it like a point mass. And for a point mass, we just used it. Moment of inertia for a point mass is mr squared. So its moment of inertia is going to be, it's 0.9 meters away from the axis, and it has a mass of 0.25, so 0.25 times 0.9 squared. 0.25 times 0.9 squared. Calculator says 0.25 times 0.9 squared is 0.2025. 0.2025. And that's in kilogram meters squared as well. Those units definitely have to match if we're going to add them. So then the total moment of inertia of this system is now 5.2025, and omega final can now be solved for. Divide by 5.2025 on both sides. 5 times 7 divided by 5.2025 gives me omega final as 6.727, I'm going to say 6.73 radians per second. I know it comes out as radians per second because radians per second is what went in. What goes in is what comes out as long as the units for the other thing going in match, which they do. Kilogram meters squared and kilogram meters squared. Those units cancel out. All right. Let's see what's next. We've got 2 more. Can I fit them in these last 15-ish minutes before I have to get going? 51 says, the puck in the figure has a mass of 0.12 kilograms. Its original distance from the center of rotation is 40 centimeters. Let me actually put this one in front of you guys. So that's the figure that they're referring to. So the puck has a mass of 0.12 kilograms, and it starts 40 centimeters away from the center of this table or whatever it is. Let's see, it moves with a speed of 80 centimeters per second. The string is pulled down 15 centimeters through the hole in the frictionless table. Determine the work done on the puck, and then the hint is consider the change in kinetic energy of the puck. So that hint is pretty much the same as the hint that we got with that other problem with the spinning top. It's pretty much alluding to the same relationship. Let's go ahead and see what we can do with this one. Maybe I can fit it all on this one sheet. What's left of it anyway. Okay, so mass is 0.12 kilograms. I guess I'll draw it over here. There's your puck. It has a mass of 0.12 kilograms. It goes around in a circular path on this surface, and then the surface has some sort of hole in it, and then through that hole is a string that can get pulled down. And let's see, so mass 0.12 kilograms, mass 0.12 kilograms. What other data do we have? Its original distance from the center of rotation is 40 centimeters. So I'm going to call that R initial equals 40 centimeters, or 0.4 if you convert it to meters. And it moves with a speed of 80 centimeters per second. So V initial is 80 centimeters per second, or 0.8 meters per second. The string is pulled down 15 centimeters through the hole in the frictionless table. So I guess we'll call that delta R is 15 centimeters, or 0.15 meters. Determine the work done on the puck. Determine the work done on the puck. Okay, so clearly there's some force that's being exerted here. The hand applies some sort of force. That force results in a tension that pulls back on the hand, but also there's a reaction to that tension force that ends up pulling inward on the puck. So there's some sort of force of tension there. Now, this force of tension creates no torque. That's the important thing to note here. This tension force does not create any torque on the puck. Why? Because the axis of rotation for the puck is through the table, and the direction of the tension force is towards that axis of rotation. The lever arm is going to be from the axis of rotation to the point where the force is applied, so the lever arm would be that way. The angle between the lever arm and the force is 180 degrees, so the torque due to the tension force would be R times the tension force times sine of 180. Sine of 180 degrees is 0. So there's no torque due to this string or rope or whatever they called it. They called it a string. There's no torque due to the tension in this string. So there's no net external torque acting on this puck. The only other forces acting on the puck, since the table is frictionless, would be normal force and gravitational force, but those cancel each other out. So they're not exerting any net torque on this thing either. So net external torque is 0. Angular momentum is conserved. Which means we can actually figure out what the final speed of this puck is. First, let's figure out its final radius. So our final, that's going to be pretty simple. If the string is pulled 15 centimeters and it was originally 40 centimeters, then it's gone down by 15. So 40 minus 15 is 25 centimeters, or 0.25 in meters. And now we can just apply conservation of angular momentum. We can use the point mass version of it, because this puck has an axis of rotation that does not go through it. The axis of rotation is right here through the table. Does not go through the puck. So the puck can be treated as a point mass. L initial equals L final. We can use the MVR version of the equation. M V initial R initial equals M V final R final. I would call them M initial and M final, but the mass doesn't change, so it cancels out. And now we can calculate V final. Let's see. So we have 0.8 and 0.4. 0.8 times 0.4 equals whatever V final is times 0.15. Or no, not 0.15, 0.25 rather. And if I divide both sides by 0.25, 0.8 times 0.4 divided by 0.25 gives me 1.28. V final equals 1.28 meters per second. And now we can calculate the work that was done on this thing by pulling on it through a string. So work done, the total work is just the work due to tension. The work due to the normal force and the work due to gravity are going to be 0 because the puck moves perpendicular to the direction of normal force and gravity. And even if it didn't, whatever work would have been done by gravity is canceled by whatever work is done by the normal force. So either way, total work from the normal force and gravitational force don't need to be considered. The total work left is just the tension work, and that is equal to the change in kinetic energy because of the work kinetic energy theorem. And we can calculate the change in kinetic energy. It's 1/2 mv final squared minus 1/2 mv initial squared. That is barely even legible. I can factor out the 1/2 m. 1/2, and then what was m again? 0.12. And then v final squared minus v initial squared. So that's going to be 1.28 squared minus 0.8 squared. Close that bracket. Let's see, half of 0.12 is 0.06, and then 1.28 squared minus 0.8 squared is 0.9984. So 0.9984 times .06 is 0.059904. I'm just going to round that to 0.06. So I'm getting work equals 0.06 joules. And it came out positive, which makes sense. If you pull on the string and the puck speeds up, then you have added energy to the puck. So yeah, it does make sense that the work comes out positive in this case. And there we have it. That leaves us with one final problem to look at. And this one actually does not have any numbers to go with it. Let's go ahead and wrap up with this one. So, we have a cylinder with moment of inertia I1 rotates with angular velocity omega 0. Actually, let me show you this one. So there's the drawing for it. It says a cylinder with moment of inertia I1 rotates with angular velocity omega 0 about a frictionless vertical axle. A second cylinder with moment of inertia I2, initially not rotating, drops onto the first cylinder. Since the surfaces are rough, the two cylinders eventually reach the same angular speed omega. Calculate what that angular speed is and show that kinetic energy is lost in this situation, and calculate the ratio of the final to the initial kinetic energy. All right, so we have disk with moment of inertia I1. And another disk gets dropped onto it. This one is already rotating at omega 0. This one is initially not rotating. This one gets dropped on. I guess I'll draw double arrows there. So this one gets dropped on, very similar to what we saw earlier with the piece of putty being dropped onto a spinning cylinder. And eventually, sometime later, we get the following picture. I'll draw the top one first so I don't mess up this drawing. There we go. And together they both spin at a rate of omega, new rate of just plain omega. All right, so let me reread and see if there's anything else we need to consider here. So this thing has a moment of inertia of I1. This thing has a moment of inertia of I2. Okay, so that's pretty much it. Calculate omega and calculate the ratio of the final kinetic energy to the initial. Okay, so let's get a formula for omega. So for this thing that's just dropping directly down, exerting a torque directly downward, or sorry, exerting a force directly downward is not going to create any sort of external torque because, well, the torque would be parallel to the axis of rotation, but also because whatever torque this collision would have exerted, it would have exerted equal amounts on both, and that's still within the system. It's not external, so no problems there. I don't see any sort of outside forces involved in this interaction. All the forces in this problem and torques resulting from those forces are caused by the two objects on each other. So our net external torque is still 0. We can apply conservation of angular momentum here. Let's see, so that would be L initial equals L final. So I guess this time I'll just write it kind of the way you would traditionally do it for linear collisions. I1 omega 0 plus I2 times, well, it had 0 angular speed in the beginning, equals I1 times omega plus I2 times omega, which is essentially just I1 plus I2 all times omega. I1 plus I2 all times omega. From there, it's actually really easy to do part A. Just divide by I1 plus I2 on both sides, and you have it. Omega is equal to I1 times omega 0 over I1 plus I2. That's it. We used the given constants of the problem to derive our expression. That's all we need to do. If you introduced any new variables that weren't given in the problem, then you'd have to find a way to eliminate those and simplify, but we didn't have to do that here, so we're already done with part A. Part B, show that kinetic energy is lost and calculate the ratio. So we can actually do both of those things at the same time. That would be, because one way to show that kinetic energy is lost is to show that the ratio of final to initial kinetic energy is less than 1. The other way you could do it, which might be easier depending on how the math ends up looking, is you could just compare kinetic energy initial to final and see whether or not a less than, greater than, or equal sign goes in between the two. Let's go ahead and see what we can do with the kinetic energies. So first let's derive expressions for both. So kinetic energy initial is equal to, well, this thing isn't really going to have any sort of initial kinetic energy. It's just dropped onto the other disk when it has no rotation in the beginning. I1 has a starting kinetic energy of 1/2 I1 omega 0 squared. And that's it. In the final state, kinetic energy final is equal to 1/2 I1 plus I2, both of them essentially move as a single unit, times their angular speed of omega squared. Now, for the sake of comparison, we can substitute omega squared with this expression squared. So I can do KE final equals 1/2 I1 plus I2 times, oh boy, we're going to have I1 squared over I1 plus I2 squared times omega 0 squared. Okay, we can cancel I1 plus I2 with one of the I1 plus I2s down here, so now that one isn't squared anymore. And from there, my best bet would be to just go ahead and calculate that ratio that they were telling us to try and find. So I'm going to do KE final over KE initial equals, let's see, we're left with 1/2 and then I1 squared over I1 plus I2 times omega 0 squared over the initial kinetic energy was 1/2 I1 omega 0 squared. We can cancel the 1/2. We can cancel omega 0 squared. We can cancel one of the I1s. And we are left with I1 over I1 plus I2. Okay, so all we need to do to prove that kinetic energy final is less than kinetic energy initial is show that KE final over KE initial is less than 1. If this ratio is less than 1, then the thing on the top must be smaller than the thing on the bottom. So in other words, all we have to do is show that I1 over I1 plus I2 is less than 1. I1 over I1 plus I2 is less than 1. And that's easily proven because if we multiply both sides by I1 plus I2, then we're left with I1 less than I1 plus I2, which is true because if you subtract I1 on both sides, you're left with 0 is less than I2, which is most certainly true. I2 cannot be negative, and it's definitely not 0, so there you go. We have proven it. Since I2 is greater than 0, it follows that I1 is... wait, hold on. Let me reword that. Since I2 is greater than 0, it follows that I1 plus I2 is greater than I1. Therefore, 1 is greater than I1 over I1 plus 2. And since this ratio is equal to kinetic energy final over kinetic energy initial, then 1 must be greater than the ratio of final to kinetic energy. Therefore, the final kinetic energy is less than the initial kinetic energy. I know that's kind of wordy, and that's probably overkill even for the AP exam, but if you really wanted to make it extra clear to the graders that you know what you're doing and you know what your result means, then if you had the spare time on your exam, I guess you could write that entire essay for them. And I'm sure whichever grader has the fortune or misfortune of looking at that will go, okay, I get it. You know what you're doing. Here, have the points. But maybe that's all in my head. Anyway, I think that'll be enough for today. I actually had 2 more interesting problems that I wanted to consider. One that I remember, I think it might have been from an old AP exam, and another one that I came across on the internet that had me thinking, but I might just make a separate video for those 2 problems because they touch on a very, very important concept involving rotational kinetic energy. But if that video comes out, you'll see it. Anyway, I think that'll be it for today. So hopefully this has been helpful. Take care, and I'll figure out what it is I want to do next week. Maybe I'll do some math instead, or maybe it'll just be more physics. Maybe even some chemistry. I don't even know yet, but I'll pick something. Anyway, see you guys later. Come back next week for more. Or don't, if this has sufficiently intimidated you. See ya.